So, welcome everybody. Namaskara. This is the second public talk for the IIA Open Day by Professor Annapurni Subramaniam. Some of you might have heard of her. She's a director of this institute. She also won the Vigyan Shri, the first Vigyan Shri award last year. And many other awards as well. Her work is on binary stars, the Magellanic Cloud, satellite galaxies of ours, and strange and weird things stars do when they have a brother or sister, like many of you might have experienced yourself. And today she's going to talk about binary stars, what happens when one star is slightly hungry, eats from the other star, what happens when they merge and they form new elements of the universe, many of which you're probably wearing on your hands or neck right now. So it'll be a fascinating talk about all of that. So, Prof. Annapurni Subramaniam, please go ahead. And at the end of it, we'll have time for question answers.
How much time I have?
40.
Thank you. Good afternoon, and thank you all for coming over here for this open day. And I just wanted to know how many of you have gone around seeing the stalls already? Can you raise your hand, please? Okay, roughly half. And so some of you, please go around and see the stalls as well. So the title of my talk looks like Stellar Tango, from binary orbits to blazing merger. So that's the title of it, but then I'll spend some time telling you about this institute and also what the fundamentals are about astronomy and why we should be studying the stars and why these binary stars are important. So so that is the kind of the layout of the talk. So so can any one of you tell me what is this picture in the slide here?
Space.
This is sky, right? It's a sky picture. So sky picture, there's a pattern you see there, right? So that is one. And what is this?
A bit low volume at the back.
All right. Is it better?
Can people at the back hear?
I have to hold like this? Oh my God, okay. No, but I'll have to hold it because this is literally, I can't turn like this because I might also have to turn with my head, right? So it's all right. Yeah. I have to hold too, but then it's all right. So this will work. So, what I was telling you is that there is an object over here. What is this? Okay, I will call it as a telescope. The observatory would mean entirety, right? All the infrastructure over there, everything together is an observatory. So that's one telescope. There could be many telescopes in an observatory as you see it. So, so let's just get everybody on the same page. So that's why I started off with this. This is a telescope on the mountain of, it's called Mount Saraswati in Hanle. It is called Hanle. It is in Ladakh. And now this patch of the sky, you can see it. Can anyone tell me what it is? Milky Way. So why do you see the Milky Way like this? Okay, that is one. Second, it is a zoom, actually like a SLR camera, which is an astrophotograph, right? So this is not the photograph that is taken from the telescope. This is the photograph taken of the telescope with the background sky. So this is the telescope. If we have it in the field station, we operate that field station. It's called the Indian Astronomical Observatory. It is one of the highest observatory in the world and highest in India. It's at 4,500 meters above sea level. And the peculiarity is there's hardly any pollution, as he was saying. And also the cloud coverage is minimal. So there's no monsoon clouds going over there. So when 365 days, we can actually operate it. But under very harsh conditions because it's a desert, high altitude desert, and hardly any oxygen. There's no water vapor, there's no oxygen. So its climate conditions are very harsh, but it's absolutely brilliant for astronomy because you can see the sky very clearly. Now, in this picture itself, you can see dark patches and the bright patches, right? So what is it we are seeing? It is actually we are seeing towards the Milky Way. So if you have the Milky Way like this, let's say, assume that this is a disk. I'm sorry, this is a rectangle. Imagine that this is a circle. In which case, if you see this is called face on. If you see it, edge on. The same one, if you see it, then you'll see a kind of a stretched part, right? That is what you're seeing here. So this means that if you look into the galaxy, you can see many dust particles. You can also see stars. So what is in a galaxy? It can be stars, dust, gas, etc. Everything together we are seeing there. Where there is a large amount of dust, the light is not able to come through, there you see dark patches. We also see, stars being formed here, different colors, etc. I'll example. You can, this particular structure is very, very bright. So a lot of stars are formed. So what we're talking about is that how stars are formed. And when they form, how they form in groups and singles, etc. So that's the whole theme of about it. So let me move on to the next slide. Yeah. So give history of this institute. Just shifting the gear. You might have seen the library exhibit. If you're not, please go and see it there. The history of this institute is we trace our origin back to an observatory set up in Madras in 1786. And it was moved to a permanent setup in Madras itself in 1792. And it operated till there, till 1899. A lot of work has happened in between that you can see from there. Previously, if you see, how do you find your location? Astronomy is, basic fundamentally, mankind looked at the sky, it's an ancient science, is because you need to know the time and location. Time you see by looking at the sun, the daily motions, the moon, the monthly motions, and yearly motions of the stars. That's how you know it. How do you know it? There's an exhibit out there down. You can go and look at the instruments which were used. There are some models there. You can see it. But by then, we can actually use telescopes to see it. So how telescopes were used in the early part, you can see in that particular booth. 1899, we set up the Kodaikanal Observatory, particularly to study the sun. Why to study the sun? Because we came to know that there is the climatic conditions moderating and there are sunspots. And that time spectroscopy has been invented. They started seeing lines in the spectrum of the sun. They started realizing that, taking the spectrum of the sun, you can actually understand the chemistry of it. There's an exhibit in the Survey of India office where you can see the spectrum of the sun. So those kind of activities require stable sky conditions. So just move to Kodaikanal. Then we set up this particular field station, this particular center in 1971. Then we headquarters also moved, and we came under the Department of Science and Technology. There are several ancient handwritten manuscripts are also with us. So please look at the library one for this. So we have a ancient heritage of, this is the kind of heritage of, or the history of astronomy in the country itself, because a whole lot of things have gone in there. I should also mention that between this period, there was an eclipse in 1868, which was done in Machilipatnam and Guntur. It was observed from there, and at the time spectroscopy was invented. They looked at the solar corona, and that they found a line near sodium. They did not know what it was. That is the first detection of helium. So helium was detected there in that experiment, and that led to the discovery of helium. And the name helium relates to helio with the sun, meaning first is found in the sun. So what do we do now? We have several field stations. We are sitting here. We continue to operate the Kodaikanal Observatory. We have Wildlife Observatory Kavalur. There's a booth there, you can see it. We also have this Hanle, the first picture I showed. But when it was established in 2000, people could not go there to take data. So actually, we have a station in Hosakote. People go there and actually remotely operate the telescope. So it is not for everybody, you cannot go to that height and take data. So that is also good. But we also have, in the center, we have two payload made, integrated and launched. These two are also exhibited downstairs. You can take a look at it. You wait on AstroSat as well as VLC on Aditya L1. We also have a radio observatory Gauri. And we're also building up a planetarium in Mysore. This will be inaugurated in the next few months. It will be operational soon. So if you visit Mysore later part of this year, you'll be able to see the LED dome planetarium. We also have a partner to the India TMT, and we have a India TMT coordination center. You might have seen a booth where it displays how the mirrors are produced for that. So this is the footprint and the space print we have for this particular institute. So large amount of astronomy engineering also goes into it, because huge amount of engineering requirements are there, not only to build it, but also to maintain it and operate it. Now, this is a picture of the Indian Astronomical Observatory. This is the observatory, okay, because you have this is the Himalayan Chandra telescope. This is another telescope out there. There are, communication channels. There's on the ground. This is the hilltop. On the base camp, we have a Hagar telescope. It's a gamma ray telescope. This is also a Maze telescope. It's also a gamma ray telescope. Everything together becomes an observatory. So that's the difference between a telescope and an observatory. The observatory can have multiple telescopes. Now I'll show you a video of the mountain top so you can get a feel of it. So this is the mountain top of IIA. We have a couple of telescopes there. And this is the Himalayan Chandra telescope established in 2000. It is operated for the last 25 years. And these are the instruments inside. And since it is actually remotely operated, all the instruments are mounted. There's no time to change from one to the other. And you can see them rotating. And there is also an instrument below this telescope that you will see. This is a spectrograph, which takes high resolution data for elemental studies, actually. And this is another telescope, which is jointly operated with IIT Bombay. And this is the base where we have HAGA, High Altitude Gamma Ray Telescope, as well as the maze, which you will see now. So this is a maze, 21-meter major atmospheric Challenger telescope. This is an experiment by Baba Atomic Research Center. So they operate this in our campus. And there's no power grid there. All the power is coming from the solar panels. So this is actually a green. It's been established so far like this only. We do have generators. We have a load which can go beyond that. That is operated based on that. So moving on. This is the Kavulur Observatory. In stark contrast, that was a barren land. You can see a lot of green trees here. This is set up in 1960s, and this is the 2.3-meter telescope. That time it was indigenously built in 85. It was inaugurated. This is near Vellore. And this observatory actually is open for public every Saturday. It's an open day. So every Saturday, any Saturday, if you plan to go there, please, you can go into the observatory and see the telescope, etc. And there are a lot of exhibits will also be there. So there is actually, I'm playing a movie, but the booth, if you go, they also have a drone photo shoot of the entire thing. Here also you can see multiple telescopes. This is also an observatory where all these domes correspond to multiple telescopes. So observatory will be a ecosystem of everything together. So I'm not going into the details. I'll go. Each telescope has its own instruments, and these are the pathways. Kodaikanal Observatory was established in, as I mentioned, 1899. And now you can ask, what did we do with the data? What are we doing? So you can actually, these are the daily images. These are like typical images we get of the sun. And you can actually, what are we looking at the sun disk? You can see the sunspots. These are moving. And as the sun rotates, the sunspots also move around. So this number of sunspots change with respect to activity of the sun. And sometimes it can be grouped, and it can result in the coronal mass ejections. Now, we can actually study the number of sunspots or the area of sunspots or location of sunspots over the period. So for that, you need to actually have a lot of data. So if you plot all the data over the years, you can actually see that this makes something called a butterfly diagram, which means that the sunspots start from higher latitudes and move towards the equator during its activity cycle. So it comes like this, from north to the equator, south to the equator. So together it becomes a butterfly. Again, the next cycle starts, it does the same thing. Because we have 100 years of data, we can do that. And the most important thing which you can notice is that the activity is not the same in each a cycle. So there's a variation. So it's still the physics behind why is it happening, how is it happening, is still being worked out. We still don't understand quite about it. But this data is very unique from that point of view. There is a video on the most...
Welcome to the Kodaikanal Solar Observatory, a celestial window that's been observing the sun for an incredible 125 years. Let's take you on a journey through time and explore the history of the observatory as well as its instruments and its legacy. The Madras Observatory, established in 1792 by the East India Company, did outstanding work for more than a century. Following the suggestion of the Indian Observatories Committee, Kodaikanal was chosen as the ideal location for a new facility to study the sun. The Solar Physics Observatory at Kodaikanal was born on 1st April 1899. The observatory started functioning with a 6-inch telescope to image the sun in white light as drawings and then as photographs. A spectroheliograph was also employed to image the sun in H alpha and calcium K lines. Both instruments function to this day. The observatory soon attained international prominence after John Evershed joined Kodaikanal in 1907 as the chief astronomer. In January 1909, he was measuring the Doppler shift in spectra across sunspots using the spectroheliograph he had built at Kodaikanal when he discovered that the gas flowed radially outwards in sunspots on the photosphere of the sun. This phenomenon is now termed the Evershed effect. A stamp was issued on the centenary of this discovery in its commemoration. The observatory has been observing the sun in white light, H alpha, and calcium K lines and has one of the oldest continuous records in the world. An older 8-inch refractor was installed in 1954. The first radio observations from India were made here in 1952. After Vainupappu became the director in 1960, he oversaw the completion of the Kodaikanal Tunnel Telescope, hosting a spectrograph which is now fitted with a spectropolarimeter. In 2014, an H-alpha telescope was installed, and soon after, the WARM telescope was installed to image the sun in G-band and in calcium K. The museum is a well-known tourist attraction, and the library hosts numerous historic scientific documents. The full digitization of all historic records of the sun was started in 2007 using a CCD camera and a uniform light source.
Publicly available, actually. We also have the radio telescope in Gauri, where we study the plasma which is coming out of the sun. So this is the normal. Previously, we have an antenna used to keep it like this, right? This is the vertical antenna. So we also have a space campus in Hosakote, and we also this is used for all the space payloads. And this is you might have, if you go to the ITOF, the 30-meter telescope booth, you can see mirrors which are being large mirrors which are being fabricated. So I have a small video of that facility as such here. You can actually see how the facility works and how you can actually polish large mirrors. Mirror handling is a very, very unique capacity. So this is a large factory scale place. So this is the round lens, basically round 1.5 meter size. So this is draper, so where you actually put it. So it comes with a small shape, but then you have to actually shape both the sides. So you have to put it and then shape on the one side. So the tool loading is there. So you have to top the back surface first. There's a tool for polishing it, because if you can't scratch the mirror with anything, random things. So you need to actually have a tool and see how much you have to take the meniscus out. And when you take it out, it has to be extremely smooth. So basically you have to scrape it, but the scrape should not leave any scratches. So the technique you need is a very, very thing. So back surface is done. Now it's inspecting all the back surfaces. Then you have to actually mark it, and then back surface is ready. Now they have to make the new surface. Then to actually bend it and polish it, these are the pads. After the pads are attached to the mirror, there's a technique by which it is done, and it's loaded onto the machine and stressed. Then you have to have the polishing tool with the tiles, then grind it. The people who make telescopes know that they have to grind the mirrors to do it, right? So this is an automatic method. Normally it takes about 6 months to make a mirror of this size. Now we can make it in 2 weeks. So it's a huge innovation out there. So as and when we polish, you have to actually measure the surface, and also the tool also has to be changed because that gets worn out. So you have to check it and do it. So very intensive work, and there's different types of polishing. This is a pitch polishing. And these are mostly a computer control. You don't have a manual intervention there. So you have to feed in all the values so that the computer takes care of most of it. Until then the polishing happens, you have to measure the thickness, and also the mirror becomes transparent. So now the tool which is attached to it has to be removed. has to be done carefully so that the mirror doesn't break. So the handling has to be very, very careful because large mirrors, I mean, even a small glass we hold, we have to be careful if you drop it breaks. So not even a chipping should happen. This also is the way you actually measure the surface of the mirror. So this is a polished one. You can see it is transparent. So this typically takes about 2 weeks. Traditionally, traditional methods take about 6 months. So there's a difference. So moving on, this is a space program which you can see the UGIT, which is from an astrosat. This instrument is up in space still. It is completed 10 years, and I worked on it as a calibration scientist. So I did a lot of science from this in the last 10 years. And these are the images which are shown here. And these images are actually false color images because ultraviolet light UV cannot see it in the eyes, right? So if you want to tell you what does an ultraviolet light look like, then what is true here? The color is not true. What is true is the intensity. How much flux I measure. So I have measured it, but I have to convey it. So I give it a color and convey it to you. So in this case, if there is a blue and yellow, you can say yellow would mean that the near UV intensity, and the blue would mean the far UV intensity. So even if you say an X-ray picture, you cannot see X-rays. So you create a picture with the intensity. So they are called false color images. So when you see an astronomy picture, they sometimes can be real color, but sometimes it can be false color as well. So you need to be aware of it. But it's true, the intensity is true. It's not a simulated or it's not a generated image. It's actually a true image. So moving on, we talked about stars being formed in the first slide. Here also external galaxies or stars are formed. So this spiral arms are full of newborn stars. Now going to where do they form stars? How do they form stars? The stars are formed like molecular clouds. These are big patch of molecular clouds. As you saw the dark patches in the Milky Way pattern, right? They're coming from the molecular. So it's a hydrogen. It can be in molecular form. They can also be other elements. I'll come to it. So this can get clumpy. The large structures, very large structures, they can be clumpy, and when the gravity takes over, they actually collapse to form stars. So that is how we understand, and also we detect it. And they become stars, and then they have a material around them because when start collapsing. What happens is may not be rotating, but some energetics can give a small angular momentum. The angular momentum needs to be conserved. When it becomes smaller, it starts rotating. Once you start rotating, the material becomes a disk around it. And sunlight starts formed in the disk when you have planets being formed. It can be planets if it is a small star, but it's a big star. They cannot, because the star evaporates everything. It's very, very high energy. Rays will come because it's high temperature, it will evaporate everything. This is how we understand. But stars can form in groups also. Like this is only one clump forming, there can be multiple clumps forming. So everything is collapsing, you get a cluster. Sometimes you get binaries. Sometimes you get triples. You can also have quadruples. So you can have single stars, you can have a group of stars. So that's the ecosystem. So how do we study them? Or let's say, what is the chemical composition of matter from the matter with the star formation starts from? Mostly it is hydrogen, a bit of helium, but the higher elements are only this much. So this is almost 75% is hydrogen only. So it's a large amount of hydrogen is there. Even the universe, the whole composition is like this. You have only very small fraction of large elements. Now the question is, who is making these elements? How are these elements being formed? Right? So you can see that this is when the initial Big Bang happened, there were only hydrogen and helium and some initial stages, and then the composition increased, and we have the current composition like that. So how did you start forming elements? When the solar system formed, where are the elements? Even we are made of elements. Where are they? Who is making it? We are not making any elements. How did it form? So that's the question we are trying to answer. And most abundant is hydrogen, and then helium. Now, as I mentioned, the stars can form in atomic hydrogen clouds, or atomic hydrogen clouds become molecular clouds. As you saw in the Milky Way patch, all these branches and somewhere the stars are being formed, right? So the star formation happens. You would have seen pictures of this, the village of creation. And then the massive stars form, also small stars form. The massive stars die immediately. that's like supernovae, and then they eject the matter into the interstellar medium, and then this ejecta gets mixed up, and the whole star-gas-star cycle turns. So when the whole thing turns, what happens is your pollution increases. Exactly like the number of cars going on the road increases the pollution in the gas around you. Exactly the same thing happens. Who's the pollutant here?
High elements.
Who's polluting?
Stars.
Stars will be the polluters, of course. Why are the stars are polluting? No. Why are they polluting? Because they're cooking elements, right? If they're made from same matter and threw out the same matter out, they're not polluting. The cars are not doing it, right? The cars are actually generating. Basically splitting the material, and they're not generating anything, splitting it into a harmful material and ejecting it. Here, they're not doing it. They're actually making new elements. The question is, how are they making the new elements? Why are they making the elements? Can they make all the elements we see around? Right? So that's the question. So this cycle is important. Even as we in the sun and the solar neighborhood, we have certain elements. I see it. Who made those elements?
Stars.
They are all made by the stars which died before the sun was born. They have to form, cook, and disperse and die so that the next generation forms will have more elements in it. So for life to sustain, those elements are important. So if you see around, the chemistry left behind, it's a signature. So how do we study? So that is the reason you need to study those spectral lines you see in the stars, which tell you what is the composition of the star, and then you look at yourself around the solar neighborhood. Do we have the same composition? Sometimes yes, sometimes no. Then you are asking questions, well, how did that element come there, and why don't we have that element? So those questions come. So that's how the whole question of how the system evolves and how the chemistry is even evolving. You need to find out that. This is the basics of it. So if you have stars of various masses are formed, the small mass cannot burn much, it ends up as brown dwarf. Again, sun-like stars will end up like a white dwarf. Now, when it dies like a white dwarf, the outer layer of the star gets mixed up. But it takes about quite a bit of time, right? 10 billion years. But if you go to supernovae, like this very massive star, they become neutron stars and black hole as supernovae. And so what I'm trying to say is that this cycle, time required to cycle, this churn, is not the same for all the mass stars. The more massive stars, the cycle turns very, very fast. So that means the elements produced by massive stars get mixed very, very fast. The rate of production is large. But the small stars, the cycle is turning slow because sun takes a long time to evolve. So they pile up. So the time scale is different. So they all add up to the chemistry of it. So here is the picture representing it. So how do we know how stars, which are the different types of stars? What do we even measure if you look at it? Let's say look at this star. How do we even study it? I've given you a question, how do you even study it, right? So you can look at the sun. How do I even study the sun? What can you measure from the sun? You can see the brightness, right? There's a lamp there, I need to look at the lumen of that lamp. So you can study the brightness of it. You also can measure the temperature of it. A yellow lamp will be warmer than a blue lamp, or rather see it, but actually it's hotter is the blue one. Blue flame and red flame. In gas, you know that a blue flame will be temperature will get more, right? So blue stars in the sky are hotter than the red stars like BTUs. So something like that. So you can actually measure the temperature and the brightness. Now, can it be a fundamental parameter? Just the brightness of the star and the temperature? Yes. Why? Why should it be a fundamental parameter? The temperature of the star is determined by what? The energy it can produce and how it can transfer that energy to the outside, right? It also is related to the brightness it can produce. The brightness also can be more if it is bigger. The smaller will have, because surface area is more important there. So it is related to that. So if you actually put it together, you will get a sequence. This is called the main sequence. So we see that the sun is sitting here, somewhere here, and you have giants, supergiants, and white dwarfs. These are the things. Now, if you look at the inside of stars, this is how it's called the onion skin model. If you cut an onion, you'll see layers, no? So you can imagine that. So here it will be, inner part will be carbon, then it can be helium. So this is how the stars make elements. This is called fusion. So when hydrogen atom fuse together, you get helium. Helium fuse together, you get carbon. Like that, you make more and more elements. So now your story is complete. Now you just fuse everything together, you'll get all the elements. Is the story complete? Not quite. Because I can't just fuse two hydrogen here and give you a helium. Because it can be very hot. Why? They fly apart. So the stars' interiors are extremely hot so that you can actually do the fusion. So that's what we understand. You can ask me, you just give me stories, yeah. And you expect me to believe it? How do you even know that fusion is happening? So of course we know it because when the sun is fusing hydrogen to helium, there's something else which comes from it. Anybody? Energy of course comes out. That of course comes out. It can be due to something else also. No. What exactly is the fusion doing then? Why should we say that it's fusion? Neutrinos. Have you heard of neutrinos? So the neutrinos come, and if you actually have a neutrino detector, you can see the sun's path in the neutrino detection. So that told us that yes, it is indeed fusion. Because the number of neutrinos you expect, the intensity of the number of neutrinos you get, you actually are getting it. So that we actually proved it. So we have confirmation that it is indeed fusion. Okay. So interior will have a lot of elements there. Now moving on, we can also say that can all the stars be? How do you put them? Where is black hole here? Where is there's neutron stars here? I'm not shown anything here. Where are planets here? Because they can be very cool. Here is basically temperature versus brightness, as I mentioned. You can also have just the mass versus its size. Because when you talk about black hole, it can be any of mass, but the most thing is how densely you have packed that matter. So you have Earth, which is a mass, but the radius is also less. But when you move forward, this line gives you all the stellar systems. They are hydrodynamically stable. Whole huge systems, but they're stable. And you go to this side, you have white dwarfs with neutron stars and then black hole. And that's it, it is stellar nurseries. Now, these are basically because of single stars. You can also have chaotic things going on when there are 2 stars, 3 stars come together. So I'll come back to it. So, as I mentioned, this is the crux of the matter. Any star can go up to iron. You make carbon, oxygen, more and more. Till when you can go? Till iron. Why? Why? So, yeah. So why does it do that? The question is, it cannot produce any more. It cannot. Two iron nuclide cannot coalesce. It has been happening because you release the energy out of it. It's called binding energy per nucleon. This is the binding energy per nucleon. You see this, it keeps increasing. And then after iron, it just falls down. Okay, so you need to actually give it energy to do it. To fuse together, if you put hydrogen and make it to helium, some of energy is released as well as particles are released. Now you have to give energy for fusion. That's not possible. It is energy generating system, not energy. You cannot give energy to it, right? So because of that, this kind of a fusion, the star, a single star, cannot produce anything more than iron by fusion. This is like this. Why? Because you are releasing energy in a fusion mechanism. So fusion can produce only up to iron. But there are more elements after iron, right? We do see them. So there must be other mechanisms. So what are the other mechanisms? This is a periodic table. Everybody would know it. This is different types of elements, which is colored based on what elements produce what. So we can see it, these are coming from Big Bang, these are large stars, these are small stars, these are supernovae, and only this much is man-made. And if you go on to this particular part, it will become very unstable. They're only alive for a very, very small time. It actually decays into other stable elements. So iron is somewhere here. The rest of them all you have to form. Where are they forming? So that is where, so the heavy elements, fusion in massive stars ends with iron, and then rest of them have formed with neutron capture. So if you have iron, and then you have a lot of neutrons present and protons and neutrons present, This nuclei captures these neutrons and protons and make higher elements and also isotopes. So if you actually see them, you will not only detect the element but also see the environment. It's basically nuclear reactors, high-end nuclear reactors where you have a lot of neutron. In normal reactors we control those neutrons, but here it's uncontrolled neutron, so you can actually produce many elements from it. So coming to it, these are all exploding neutron stars and white dwarfs you get. This is another way where dying stars and human synthesis is coming here. But exploding white dwarfs, merging neutron stars, etc. are there. So this corresponds to stars which have to come together. So this requires the binaries. So single stars can produce to some extent. And after iron, you need exotic environments to produce other elements, not just single stars. Some more is required. So to populate the popular periodic table, you need more than just single stars. That's the bottom line. Now, where do you find them? As I mentioned, this is an open cluster. This is a globular cluster. I study both of these kind of systems. Pleiades up in the sky. Anybody know Pleiades, Hyades? So they are clusters. They are nearby clusters. PSP. So they are all clusters. And these groups of stars are long binaries. So, so what is a binary? How do you even know that they are binaries? So you can see these things. So these are the binary systems. They go around each other. And so you can see this is you can see in terms of light curve, like eclipses, or in terms of velocity. That Doppler shift, you understand Doppler shift, right? So if the star is coming to, this is observer. So this is going like this. Now this star is coming towards you, this is moving like this. So the spectral lines get shifted. One is red shifted to blue shifted towards you, the other is red shifted. So the spectral lines keep moving like this over a period of time. So you know that the star is going back and forth. The spectral line shift of this is because the star is moving back and forth. So you can also have one going in front of the other. You go to an exhibit downstairs, you have a light curve actually being shown there, how the light curve comes. This tells you the period at how fast it is going around. This also tells period, but it also tells you how fast it is moving. Velocity it also gives you. Why velocity is needed? It tells you the mass within. So it's an extremely important tool. The same thing is used to even detect exoplanets. Radial velocity. So just simple Doppler measurements are extreme, but very, very high precision measurements are needed to understand that. So once you do it, you can actually find out their velocity and where will you use it. So I'll come back to it. Sorry. So you can actually see the light curves. Maybe I'll just explain this symbol. You can also have these two stars. Either once they are close together, you can actually matter can be transferred from one to the other. So what happened to these stars going around? It can actually suck the matter from one to the other. So I have studied binary stars and they call blue stragglers. One ends its life and the other becomes more massive. These are rejuvenated stars. So they have different chemistry as well. So sometimes in these systems, they come and merge, like the dense stellar systems which I showed you earlier. This one is so dense that the stars can actually come and collide. This is the globular clusters are the only place where stars collide. Our sun has not collided with anything so far because the planetary system is still existing. But stars in this actually collide. So these are very rare systems, but they do collide. And in this case, this collision and they become one star. And if it is massive stars, you can actually have exotic systems going on there. And this can be, these are the debris and things like that will be there. But in single stars also, they can merge, like the binary merge. I'll have a picture of it as well. So they either can be mass transfer binaries or merger binaries. So in one of my work, just wanted to give a glimpse of it. We actually looked at this star as transferring the mass to this star. And this got a period of 2000 days. And as I mentioned, you saw some elements being created right out in the outer part of the star. Those elements will be transferred to the star. So though it will look like a normal star, but will have other chemistry. So we chase it up. And using spectroscopy, this is the master's thesis, one of the students, and he actually created this cartoon where this fellow is actually taking the barium material out and becomes a barium star. The normal stars will not have barium, but the barium is produced by that star and it took it out. So that is one. But coming to how do you find black holes in binary systems? Because black holes don't emit light, but you can actually see the presence of it by the star which is going around it. If it's a white hole, it will be going slower, but if it's a black hole, the more mass and smaller radius, so it will go it has to go faster. So you can actually see the radial velocity curve. You don't see the black hole, but you are measuring the Doppler shift. You can actually see it and estimate its mass. So this is from Kareem's work at Caltech. Again, same thing, they have detected it. So you can also see its position changing and the velocity. This light curve is also very weird. It will just accelerate and come. So because of that, they detect it. And so what happens in binary system is this. So these kind of black holes can actually merge. And that is when the gravitational waves are also created. And with the LIGO detections, the LIGO system which is coming up, gravitational wave detection system is detected. Now, 10 years ago, if it asked me the gravitational waves get detected, everything possible. Now we know that technically and technologically we are capable enough to actually measure the distortions in the space-time created by binary mergers. So these are like the two stars which can actually become big, just like I mentioned, the mass can be transferred. If they are very massive stars of the like 20, 30 solar mass stars, it actually one becomes a black hole. The other can also become a black hole and eventually they can merge. So we have models which can actually see that it can merge. But in this case, how do you bring the two stars together? You can also have a third star taking away the energy. These are interactions exchanged. So this can actually happen. Now, this is a famous picture you would have seen, right? If you want to know how this picture is made and why it looks like this, see one of the stalls. It is in the Subway of India campus. So they have actually a demonstration of why a black hole looks like this. Go over and see it. This particular one. So this is exactly what the merger of black holes ring down happens, and this ring down is what we measure in the interferometric measurements, and this is how it happens. Now, why should I care about it? There are also neutron star mergers. When the neutron star mergers happen, there are plenty of neutrons. As I mentioned, neutrons are required to make more and more elements. So these elements are actually made in neutron star mergers. So similar cases where you can actually make the stars become binary here, and then they merge at the end instead of black hole, it is neutron stars. So they become different elements. So this is how this various R process elements are. These are called rapid neutron capture because they're very, very fast process. In other cases, barium and all, it's just a slow process actually. So eventually you can have the proton capture also is possible, neutron capture is also possible. So up to here you can have up to iron, you can have stellar burning. Only these many you're using stellar burning as fusion. But rest of them you're producing it as neutron capture as well as proton capture, etc. in binary systems as well as in exotic environments. So the entire system is populated by this. You can see that exotic environments take up most of it, where the fusion takes up some part of it. But you have to have this for this to take over. Otherwise, they cannot happen. So the stellar fusion is important, but over and above, the binaries contribute to it. Now, fundamentally, why we care about it is because all the elements we have is formed from stars because we can't produce anything else. We can't form phosphorus, etc. We can break down some components into something. We cannot create those elements. So it has to be formed out in the space, and that is how the things are. Thank you for listening. Yeah, questions. Just here one there.
I've got three questions, very quick questions. You mentioned period, 2000 odd days. So what is the period?
So basically, one round around this binary system.
Yeah.
So the period of completion of one orbit is the period. Yeah, it's a very long period.
And you mentioned white holes. We are only familiar with black holes.
Yeah,
There are white holes too.
not white holes, white dwarfs.
Oh, white dwarfs.
Yeah, white dwarf is the end product of how sunlight stars would end their life. Yeah, these are white dwarfs.
Oh. And my final question in Indian, culture, we've got Arundhati and Pratishtha.
Yes.
Would they be classified as binary stars?
So binary stars are of two types. One is visual binary, where you can see them as visual, but here you cannot see them as visual. You can actually have to take a measurement to say that it's binary. But the other two are visual binaries. They appear to be together, yeah, and to the eye. So the actual separation could be quite large.
Actually, in one place there was the short form of the gases. There's some 1, 2, 3, 4. Those numberings. I didn't understand what are those numberings.
Can you guide me to which slide you're talking about? Maybe I should.
This one.
This one?
The front one. Yes.
Periodic table. This is periodic table.
Yeah, like 1, 3, 4, 11, 12.
Yeah, so that is the total number of you have protons and neutrons together, right? Yeah. So you will learn soon.
Hello. In one of the slides, there's a mention of exotic elements.
Sorry, yeah.
In one of the slides, there was a mention of exotic elements. Like what are those?
No, so exotic in the sense that in this table itself, you can see that up to iron you can form through fusion. So the other elements, what is the reason? How are they being formed? Because fusion cannot take anything, two iron cannot fuse together. So how are the other elements formed? So some of the elements we know the pathway, some of them we do not know. So like even here itself we know certain elements are not there, but here even mercury, lead. So those kind of elements, even all the most of the higher order elements, it's a kind of a series. So you can see that this is a series together. So our process elements are seam together, slow neutron capture together. So there's a lot of nuclear figures going into it. So most of them are exotic, yeah, gold, platinum, everything, yeah. Not in terms of how we perceive it.
Thank you. Thank you. Mine is a very layman question. You mentioned that these stars cook inside and then, these new elements are formed. So I'm just curious, these are like mini bangs, right? Like after the Big Bang, this cooking is like mini bangs.
It's not mini bang as such because these are like, if I say that the fusion is happening inside the sun, it is not a bang, it is a continuous process, a stable continuous process.
It's a
stable continuous process. It will take a long time to actually convert all the hydrogen inside the sun or inside the core of the sun to helium. Very slow, stable process.
So inherent for any ball of
No. Like if you say, I can say that the sun is producing energy by doing fusion, by combining hydrogen to helium. Is Jupiter doing that? No. Jupiter is warm, but it is actually releasing the gravitational energy.
Okay.
And the interior is not hot enough to fuse two hydrogen to make helium.
Okay. So
Yeah.
that inherent heat.
Inherent heat is related to the total mass of the object.
Okay.
Yeah, the infall mass should be enough so that the interior heats up to the extent that it can generate energy by fusion. Once it does that, it can stop the infall.
And ma'am, just two more quick questions. We're hearing a lot about rare earth elements these days, and people are going to Greenland and things like that. So I was just curious, like this exploration of Mars and things. Like, do these rare elements get formed? Can we get some new inputs on that through your observation?
We do observe a formation of lithium, etc., in stars, but they're not excavateable thing. But you can also think of going and capturing asteroids and mining asteroids. Yeah, that is already done. That's possible. But then the cost is humongous compared to what you get.
And my final question is on optics, because you spoke about this. I know, I mean, beautiful mirrors and this polishing. Is there an institute that just focuses on that science of optics and opticology, or
There are institutions, but it's more of academic studies and trying to understand optics, various types of optics, etc. We do have an optics facility and converting into whatever our usages. Yeah.
Ma'am, I have a question here.
Yeah.
Like, since I do not know much about astrophysics, but one question always haunts me, that is the velocity of light. So we studied that 3 into 10 to the power 8 meter per second, which is very finite and fundamental, and all the calculations of the electromagnetic theory is based on that. So my question is, if the origin is the sun, so is it going to vary or to some other kind of sun source like supernova? So is this parameter of the velocity of the light 3 to 10 to the power 8 is going to vary, or it is still fundamental?
It is fundamental.
So supernova, it has got different
It has nothing to
energy.
do with supernova. It's got nothing to do with supernova. It's to do with it's a fundamental thing. It's nothing to do with one of the sun. Just
Yeah.
that we are measuring we are getting the light from the sun, that's all. With that velocity, yeah.
Oh, so 3 to 10 to the power is fixed.
It's fundamental, yes.
Thank you, ma'am, for telling this. You told us a lot about the Institute of Astrophysics. Can you guide us how those who are interested can build a career around this two sets of people, one for the kids and some for the adults? What are the options available? Is there graduate programs, or what are the career options we can pursue?
So this Indian Institute of Astrophysics is primarily a research organization. So we do not have undergrad program. We are not a university. We are an autonomous body for conducting research in the specific area of astronomy and astrophysics and related areas. So we have PhD program. We also have an MTech PhD program. Even that degrees are given by other institutions. We cannot grant degrees. We are not a degree granting institution, so we don't have such things. But we have about approximately 100 students who are pursuing their PhD. Coming to career, so this is PhD part. But for younger kids who want to aspire to be astronomers, this requires, if I explain this, I mean, he was asking about what are the numbers 1, 2, 3, etc. So astronomy, though it is sounds like a story and it's like a different thing, but when you actually try to understand it and explain, it's physics and maths. The Doppler shift, understanding Doppler shift, chemistry, nuclear physics, velocity of light, measuring velocity, measuring temperature. So these are all fundamental physics and maths. So you have to actually have at least undergrad grounding on fundamentals of physics and math. You can develop astronomy parallelly, but the fundamentals have to be there, because without which you cannot, if you don't understand, you have to go on, the fundamentals is to be firmed up. So up to there, physics and math are extremely important. Of course, engineering is important. You could see so many engineering projects out there: mechanical, electronics, optics. Again, if you look at it, thermal, all these things will require physics and maths. So it is like that. So you have to have good foundation in course topics. Then you branch out anything you want in astronomy. The scene in India is very interesting and nice, because you have more. I mean, this budget also, if there's an announcement of new telescopes coming up, so there would be opportunities. We already have LIGO, which is going on, and it will be operational by 2030. We also participating in India TMT, which is the international project, this Square Kilometer Range international project. There are a lot of projects, engineering as well as science projects going on in astronomy as such, and also space science is done by ISRO. So the opportunities are quite a bit, and a lot of challenging tasks are involved in. Anybody interested, please pursue.
Yeah. So
Sorry, yeah.
somewhere over the talk, it told that a black hole, the velocity of a black hole or a binary star can be known over Doppler effect. My question is, what Doppler effect you need to know about the spectrum? So fundamentally, fundamentally,
so this is what I was telling. So you can actually you have one star going around the other. So there is a binary. You can see only one black hole. You cannot see, but because that star is going around a black hole, the velocity with which it goes around it will tell you what is the mass within. And that mass in a very small volume would be like a black hole. You're not seeing a black hole. You're seeing an implication of a black hole being there. So this is the observed one. So you can actually see how the radial velocity is changing. You can actually see the ellipticity is much. The period is 186 days. The models predict the mass to be about 10 solar mass. So that is, you don't see the black hole. You see a wide star which is going around it in a rapid speed.
From there only you like.
Yeah, so you see the companion star. The companion star, just like I mentioned the previous one, it just, sorry, this one. You will see, you don't see the second line here, you will see only one line going back and forth. Second line, you will not be able to see it. Just the one line, that velocity you'll be able to measure.
Thank you.
I have two questions.
Okay.
I have two questions
Sure.
combining into one. During the Big Bang, was it like there was nothing and then there was something? How did all those elements form? What was there before the Big Bang? And why was it hydrogen the most right now and before the most abundant metal in the universe? Hydrogen, right?
Yeah, so when the Big Bang happened, we cannot detect anything closer to it. You only know the energetics. That time, the matter and the energy were connected. Then the matter and the energy kind of decoupled. Then it started cooling. There were a lot of high energy particles and the astroparticles, etc. were there. Then the matter cooled. And then the elements started forming. Then the most easier to form is proton and neutron. So you have only one proton and electron for a hydrogen, right? So it's the easiest thing to form.
So because it was the easiest, that's why it's the most abundant.
Mostly. Then you need to have combine all these things coming together, right? You have to have two protons. They will repel each other.
Yeah, because of the.
Yeah. So how do we bring them together? It's cooling down. So probably rapidly you cannot produce them, right? The proton and electron can form together easily. Yeah. So that gives you a sense of the rapidity in which it is cooling and how easily I can bundle up more protons together.
Thank you.
So what was your second question?
Those both were
Together.
Ma'am, I have two questions.
Yeah.
So you mentioned that you worked on a lot of amazing projects. In these projects, usually what type of data sets do you work with?
So I have worked on various clusters and on the UVIT, I don't know whether UVIT is, I'm going the wrong direction. So UVIT, actually, I was the calibration scientist of that. Calibration scientist would mean that I actually predicted its performance and also calibrated its verification in OPEC. And also, I also made the tables where when you look at measure its thing, how do you actually convert it into an astronomically usable unit? So it's called calibration. So I've done that and also all the pipelines for data. So I generated the telescope captures the data, dumps it, and I converted it into a usable form and studied how the stars are formed here and also the binaries. Yeah. The data are created by using these processes. They're called data pipeline. Yeah.
Thank you, ma'am. And my second question was, a lot of people here are usually students, right? So I think a lot of people here would have their own research projects, like independent research projects. Say if they were interested in researching with a professor here, because some of my colleagues had told me that IIA provides RESS programs where like students can work with professors. If that's true, like, can students work as interns?
Yes, I think RES people are here. Anybody done RES? Yeah. So anybody VSP student here? No. You done one shadow professor? No, not it. Okay. So there are a lot of you can get in touch with the outreach or the it will be announced on the website also. There are various types of programs we engage. We don't have undergrad program, and we have for school students and younger, I mean even college students. The shadow scientist program is there. There's also 1 day, 2 day experiencing what the researcher would look like. RES research experience program, and also visitor students program there. So these are announced in the website, and regular we take students in summer generally, where the students have time as well, school students particularly. So those programs will be announced on the website. do keep a lookout for it.
Thank you, ma'am. Hi, can you go to the periodic table? I have a question.
Which periodic table? I had so many periodic tables now. I'll go, tell me when to stop.
Yeah, this one.
Okay,
This one.
not this one. Okay. This one?
Yes, sir. There technetium, which is 43rd element, near manganese and molybdenum and ruthenium.
Trust me, I can't read it out like that. Okay.
A 43rd element. It's also a very lonely human synthesized element, and it's also a very lonely radioactive element. Why is that?
61?
43.
43, okay. Technetium.
The lanthanide.
No idea. I have to go and do
lantanides
my homework. No idea.
Okay. It's also.
It's basically that you have to detect them. So certain like recently we had a paper on detection of germanium in certain things. So you have to detect spectroscopically study certain kinds of explosions, certain kinds of environment. So only then only when you detect it, it's not only detecting, you get a barcode, you get a spectrum. How do you know which lines are there? So you need to actually go back to your atomic lines library and create it and then say that, okay, these atoms are these transitions when the electrons move from one layer to the other, this kind of an energy can be produced. And this line you have seen the spectra is coming from this. So models and the observations have to match. So either we have not detected that element or enough transitions for that element is not there in our models. So it has to be looked at. Yes.
It's also a very lonely element. It's very.
Lonely in the sense that sometimes you have iron peak elements. So you get all of the iron peak when you have a neutron capture, you get all of them together. So like in the case of if you get a barium, you also get yttrium and strontium. Similarly, you have other elements which are coming as grouped. It may be in some group or the intensity or the line depth will be very, very small that you are not able to detect. So it must be a detection issue also. It's not easy to, though it's an overall summary, it's not easy to actually say how much is coming from which.
So radioactive.
Yeah, they're all. Uranium also is found, so many of them are also found. They're also radioactive. You also have isotopes of various things. So all those will tell you how this. Once you detect, then you'll have to find out what is the nuclear reaction which is behind creating it, and what is the environment which creates that.
I have
So
a
yeah,
question.
sure, yeah.
So all the models and all the orbits we have predicted here is based on classical mechanics and most of them are based on classical mechanics and relativity. So if we if we apply the quantum effects as well, maybe we can find different results because we weren't even looking for Hawking radiation and we still found it on black holes. And possibly it can give explanation for the the sun why it has the coronal ejections in it. And so, what are the possibilities you can have with quantum effects applying on it?
We are looking at macroscopic scale. We are not looking at the microscopic scale. Still macroscopic scale. And in this case, also you probably we not even will require relativity to be applied. Some cases relativity to be applied, not quantum. So you're not looking at that level. So this is like macroscopic. You don't need that.
But like small
No,
contributions to energy.
But your errors of this, you have large errors. You want to look at it here. So even understanding the mass is a large error. You're not reached the stage where microscopic variations need to be considered. We're not in that region.
Thanks.
Yeah, there's a question. Sorry.
Yeah.
There's one here.
This periodic table which you showed like just before this question. Yes. So the barium is expected to be produced in a dying low mass star, mostly during the asymptotic giant branch. You also mentioned in the one of the master's thesis project boost factor.
Yes.
Yes. But if we find the spectroscopic signature of barium in a supernova, like the spectrum of a supernova, what could it possibly indicate? Like supernova has to be doesn't really like happen around the asymptotic giant branch, and we expect usually barium to be produced from a star which has ZAMS of less than 8 or 10 solar masses.
Yeah,
Because
so
this
this is where the core doesn't become iron, it becomes a carbon oxygen. So you have generally what happens is the star is very big. The how the energy produced is, let's say we are sitting here, we are producing energy. How is the energy being circulated here? There could be particle conduction, there could be radiation or convection. Convection is only when you actually hold it and do it, right? So in these cases, normally radiation, but when the gradient becomes very much like when you boil the water, initially you can't see anything, but then suddenly the water starts boiling. That's when the convection matter itself will start moving. That happens on the surface of the sun also, right? You can have it in the giant. So when as she is mentioning, how do you know it can bring the barium onto the surface because the material actually scoops out and comes back. The material, actually the circulation brings the internal material to the surface. Then asymptotic giant branch star. But that's not going to die as supernova. So the question is, why is barium in a supernova which is dead, right? So that's the question. Supernova will have, as I mentioned, the iron core and then the rest of the elements which are formed. So it tells you the supernova what to expect, what not to expect. If you find something, then it is not gone through a single evolutionary path. Yeah, it could be I don't know what type of supernova it is. So you'll have to figure out and core collapse supernova. Sorry, you have to look at the details and figure out. You'll have to relate to the presence of other elements and then see other signatures are there. Say yttrium and strontium are also there. Then see what are scandium is there. Sorry, yeah.
Hello, ma'am. Here.
Yeah.
So I have two questions. So as you showed in the diagram that iron is the most stable element with the highest binding energy.
Yes.
So why isn't the most abundant element in the universe? Because it's the most stable, then it should be the most abundant one as well, right? Because it's not the
That's
highest
exactly
stability.
what this kid was asking, because this is the status, right? So how do you make stable does not mean easy to make. You're assuming that stable means easy to make also.
Okay.
It's not easy to make. You have to make other elements starting from hydrogen, which is the most abundant, you have to make fusion.
Okay. So
So it's a million degree Kelvin you need for hydrogen fusion. You need much more than 10 raised to 7, 10 raised to 8 degree for temperature to fuse the other elements. So it's most stable does not mean most easy to make. Easiest to make is hydrogen.
Okay, and I have a second question. So, as you said, like the binary star systems have they merge or they sometimes mass
It may or
transfer.
may not, because it close enough they may even exist without knowing the existence of the partner actually, because they go around each other because of gravity, but after some time they will not be having any interaction with each other. So there is a limit in the spacing between them.
Okay, so you mean to say the binary star systems are stable in universe?
Not really. That's what I was telling in this thing that this picture that the star, these things can evolve without a problem. This binary will evolve without any problem unless they bring together. So something has to take away the energy out of it. So if you take a binary system and leave it the way it is, energy has to be taken out to bring it closer. Either it has to be born closer to influence the evolution of the other. Otherwise, if it is far away, something has to take out the energy to bring it closer to influence.
Thank you. One last and quick question.
Three questions.
Oh,
I guess it would be really interesting question. So, the first one is about your work. So, in your work on stellar population,
oh my God, you're taking a thing out of my paper and they're asking it?
Yes, I'm following up with your work. So, yeah. What observational signatures have been most crucial in your understanding of the evolution history?
What?
they call the stellar population in the Magellan clouds. What is the most?
You're putting me in a very difficult situation because I have to explain everything for everybody to know, right? I can't be answering just to you, which is not fair to the people who are present here. So she's talking about, what I did to the nearby galaxies is, if you want to study the nearby galaxies, how do you even study it? The nearby galaxies are actually Magellanic clouds, which are in the southern hemisphere. You can see them as a cloud. The name indicates a cloud. But if you see through the telescope, you can actually separate them into single stars. Now, I used my knowledge of the stars in our galaxy, and took it to that to understand, okay, if I look at these kind of stars, how is the structure of the galaxy even defined? We can't, it's a cloud. You don't know the structure of the galaxy. So I can take a certain type of a star and find out its pattern and see that how the structure of the galaxy is done. So that is what I used. And there's something called, when I use the stars where the central core is fusing helium to carbon. So they have a particular nature, particular characteristic. So I use that characteristic to actually see what map the structure of these clouds. So that was important work.
And then I guess I'm going to skip my second question. You answered first two. The last question would be, with upcoming large survey data, how do you see stellar population studies evolving in the next decade?
Actually, it's actually in astronomy data deluge. So we use the machine learning, AI, etc., quite a bit because we generate our own models to do it, and classification is a big problem because you have too much of data out there. So even during my PhD time itself, I was using neural networks to classify spectra. So even the Slow and Digital Sky Survey, and right now we have the Vera Rubin Telescope, LSST data is coming up. It's just data deluge. We have data from ground, data from sky, this is space stations. And one important thing is there's a data democratization in astronomy, where data is made to public. So any school, college students can actually work on the data. So when I started my PhD, you need to come to an observatory or institute to get the data to start working on it. Things have changed. A simple laptop is good enough, and even the software is available. If somebody can guide, you can actually understand some amount of work you can do. So that is the state of the landscape now.
Thank you.
So on that note, we conclude this talk, and we thank Professor Annapurni Subramaniam for this wonderful talk and question and answer session. So there is an Ask an Astronomer and other things going on till 5:30. So please, you can proceed to the
Yeah, thank you all.
and the exhibits. Thank you all. Thank you.